Hello, everybody. So we've finished up our discussion of discrete probability distributions, and we are now going to move into our discussion of continuous probability distributions. So let's go ahead and get started. So we're going to start with what's known as, sorry, I'm sharing my screen here. We're going to start with what's known as the normal distribution, and that should ring a bell back from, no pun intended, but that should ring a bell back from the beginning of the course, right, when we talked about the empirical rule. And so we're going to talk about it in greater depth here. And so the normal distribution, well, first of all, it's a continuous probability distribution for a random variable x with the following properties. Mean equals median equals mode. So that middle number is the same as the mean. It also occurs at the greatest frequency. The normal curve is bell-shaped, and it is symmetric about the mean. The total area under the curve is 1, and this is a really important point because that means that any portion of the area under the curve is going to be less than 1. So we have these values between 0 and 1. The total area is 1. You can see a link between area and probability. In fact, the area under this curve is what we use to model probability when we have a normal distribution. Next point, the curve approaches the x-axis as a limit to the left and the right, but never touches. And then for those who have had some calculus in their past, the graph curves downward within 1 standard deviation of the mean. And then after that, curves upward. And those points are known as inflection points. If you want to make sense and kind of think about what all of this means here, you might think about trying to sketch based on just this description. So if here's my x-axis, and the mean equals the median equals the mode, symmetric about the mean. So the mean would be somewhere here in the middle. And then the total area is 1, bell-shaped, approaches the x-axis as a limit, but never crosses it. So it's going to get really close, infinitely close, and then it's going to come up. And then it's going to have to do that on this side as well. So it should look something like that. And we can graph probability distributions using what's known as a probability density function. And what I'd like to show you here is Desmos. So Desmos is a wonderful tool. I'll open this up here. And this right here is the curve. This is the equation of the normal distribution, or of at least the probability density function. And so it may look a little intimidating, but notice what a nice curve it gives. Now, I'm going to play with some things here. This S really should be sigma, but I don't have a Greek sigma on Desmos, so I'm using S. But it's standard deviation. And I want you to notice what happens when I mess with the values. And let me bring this down maybe a little bit. So as this S increases, right, meaning greater standard deviation, meaning that the data is spread out more, you might notice that that peak decreases, which forces more area into the tails. Think of it kind of like a balloon. Have you ever grabbed a balloon that's not completely full of air, and if you squeeze it in one place, it pops up in some other spot, right? Because that air has to go somewhere. That's sort of what the standard deviation is doing. If I increase the standard deviation, then this thing flattens out and the area is sent into the tails, okay? Well, what does the mean do? Well, that rotates this thing, okay? No, I'm sorry, I said rotate, I meant shift. It shifts this thing left or right, okay? And so there we go. The standard normal distribution, well, if you think about what Z-scores are, I know it's been kind of a blast from the past, but right, Z-scores are essentially a standardization of the normal distribution, where now our mean is independent of context. It's set up so that the mean is always 0 and standard deviation is 1. So what happens here is the cumulative area is closer to 0 for z-scores close to negative 3.49. The cumulative area increases as z-scores increase. And what you should see here, when I say increase, right, or cumulative area, we're talking about left to right. So as we move from left to right over that x-axis, we're going to see the area increase. And when we get to z equals 0, in other words, the mean, right, z equals 0 is the mean, the cumulative area is 0.5, which should make sense because we said up here that, whoops, I'm sorry guys, we said up here that the normal distribution is what? Symmetric about the mean. So if that area is increasing and the total area is 1, yeah, we should have a cumulative area of like 0.5 by the time we get to the mean. Okay? All right. As you continue moving to the right, you gain more and more area. By the time you get to about 3.5 standard deviations from the mean, your cumulative area is close to 1. So what I'm going to do is I'm going to mess with this a little more, but this time I'm going to mess with the standard normal distribution. I don't want you to get caught up too much in the mechanics of, you know, what I've written here, what the formulas may or may not look like, because frankly, those are not for you to worry about. Okay, finding these areas requires calculus. We're going to use a computational tool for all these areas. So I'm going to turn off the other one and come down here. And what I have is the standard normal curve, okay? And what I'm going to do is I'm going to play with some values. So this expression, this is an integral. You don't need to worry about that. Essentially, it's a way for me to calculate the area. And so what's going to happen is you're going to see me move from left to right. Sorry, I'm going to move this out just a little bit more so you can have a better view. Okay, let's see. All right. So as I move from left to right, I want you to keep an eye on oh, come here. I want you to keep an eye on this number here, the area, and how much is shaded, okay? So right now, I'm way out in the tail somewhere. And as I change this value of C, that C just corresponds to some value on the x-axis. And so we're gonna move from left to right. And as I do, you should start to see some area. Okay, so here I am at negative 2.5. There's the area under the curve. It's the area of that shaded region, okay? So you can just barely see it, but all this area in the tail, and keep in mind that tail goes on forever, has an area of about 0.006. And as I keep going, that area is increasing, and notice, right, my area now is 0.4. What important value am I getting close to? Well, right here, right? That value is z equals 0, right? The mean. So when I get there, I have an area of 0.5, okay? And then as I keep moving, watch what happens when I get to 3.49. So right now, again, you're watching those C's. Right now, I'm at 3.3, 3.4, 3.5, close enough. Look at that, 0.999767. To the naked eye, it looks like I've got the entire area under this curve. But I could keep going, okay? And so that's what's going on with the standard normal distribution. Again, it's a normal distribution, but everything's been standardized. Mean is 0, standard deviation is 1. All right. So what we want to be able to do is use these areas to find probabilities, because probability will be modeled by area. So what I like to do to start is simply get us used to finding areas, all right? There's not going to be any real context to this. We're not going to be putting it in some specific situation. It's simply mechanical. How do you find the area? And you can do that with a graphing calculator. You could do that with Microsoft Excel. I'm going to show you on Microsoft Excel. If you're interested in maybe the TI 83 or 84, there are certainly resources to see that as well. So let's start by drawing this. Finding areas under the normal curve. Area left of z equals 1.5. So I'm going to start by drawing this, okay? And I'm going to start again by drawing it a little bit nicer than that. Okay, so I've got my x-axis here. And here's my normal curve. Not much of a normal curve. You know what? I'm going to redo that one as well. So curve might come up like this, come down like that. Okay, so here is 0. 1.5 is going to be like over here somewhere. Okay, and again, I'm just kind of eyeballing it, but we'll call that 1.5. And we want the area to the left. Okay, the area to the left. And so what I'm going to do is I'm going to come in to Microsoft Excel and I'm going to find what that area is. So let's hop over to Excel. It's loading. And we're going to find out what that area is. Come on, Excel. You can do it. All right. And so I want, let's make this a little bit bigger here and zoom in a little. So again, I'm going to come up here to this command box. I'm going to say equals, and then normal, so normal distribution right here. And I actually have a choice. I've got the norm.dist or I have norm.s.dist. So if I'm using ZScores here, so I could default to this one. If I use norm S, Excel is going to automatically assume a standard deviation of 1 and a mean of 0. In other words, it's going to assume you're talking about Z-scores. If I use norm.dist, then I have to tell it the specific mean and standard deviation. So I'm going to actually show you this one just because you'll be able to use it throughout any context. So my x, right, was 1.5, comma, my mean is 0, my standard deviation is 1, and I want everything to the left. I do want cumulative, so I'm going to say true. And what do I get? I get 0.93319. So that area is 0.93319. Again, that's all that area in there. And that should make sense. I mean, that should at least make us, appeal to our intuition somewhat. I mean, we're a standard deviation and a half away from the mean. We know the total area is 1. We get 50% of the area by the time we get to 0. So it seems like a reasonable answer. All right, area to the right of negative 0.75. Okay, well, this one's a little different, right? Because we have the area to the right. So let's take our normal distribution. Ooh, that one's nicer than the other one. And then negative 0.75 will be over here somewhere. And I want all of this area, okay? Well, when we looked at Excel, we were stuck with that cumulative function, right? it's only going to tell me the area to the left. So for Excel, what I'm going to do is I'm going to have to recognize that when I plug this into Excel, I'm getting this area over here in the tail, the left tail. But I know that the total area is 1. So 1 minus, and then that norm dot dist negative 0.75, 0, 1, and true. So this is what Excel will look like, okay? Let's go do that. We're gonna say equals 1 minus norm dot dist, and then negative 0.75, 0, 1, and true. We get 0.77337. So 7, 7, I'll round to 4 decimal places. Why not? Okay. All right, case 3, the area between. Well, again, let's draw this out. Here's my lovely normal distribution. It might not be lovely. It's just not too ugly. Here's my negative 1.25. I'll call that 1.75. And the area that I want is all this. All right. So the area, again, I'm stuck with the features in Excel. Right? It would be nice, right, if I could tell it to go from where to where, but that's not an option, right? I've got norm dist, and that requires me to take advantage of the fact that I look at cumulative areas. So I'm going to be a little bit creative here. Similar logic as when we computed Poisson distributions, probabilities and binomial probabilities. I'm going to look at the area left of 1.75. So think about what that is going to give me. That's going to give me, well, I don't know why it's, oh, I chose a rainbow color. That's no good. Here, let's go red. That's going to give me all of this area, right? Which is too much. So I need to subtract the area left of negative 1.25. And what will that give me? Well, if I subtract that area, maybe make that green, that's all this here, right? So the only area that will be left is that area between those two values, okay? And we know how this works, right? This is a norm dist (1.75), etc., minus a norm dist negative 1.25, etc. Okay, so what are we going to get here? Let's go back to Excel and let's compute exactly that. Whoops. So norm.dist 1.75, 0, 1, true, minus, and so that first expression, I now have everything to the left of 1.75. I'm going to subtract everything to the left of negative 1.25. And what that'll leave me with is everything in between. So I get 0.85429 if I round 0.8543. 0.8543. All right. And let's just go ahead and try some more here. You know, there's these next three examples, and at this point, I would encourage you to pause and work through this example 2.8.1, okay? Seriously, pause it. Okay, hopefully you have in fact paused it and are now back. So left of negative 0.94, well, I'm just gonna eyeball that. And we want that area. And so again, using Excel, I've got negative 0.94, a mean of 0, a standard deviation of 1, and I do want everything to the left. So let's come over here and see what we get. Norm, dist, negative 0.94, comma 0, comma 1, comma true. We get 0.1736. The next one, to the right of 1.24, I'll call that 1.24. And so again, for here, right, areas to the right, we're going to do 1 minus the area left of 1.24. And so 1 minus, come over here to Excel, equals 1 minus norm dist 1.24, 0, 1, and true. We get 0.1075. I'm rounding. Okay. All right. And the last one, between. And so again, when we talk about between, right, we need to consider that as area. So the area that we want is going to be the area left of 2.1 minus the area left of negative 1.7. And again, I'm going to use Excel to compute exactly those two values and therefore the difference, okay? The area left of 2.1, right? That's all this. But that gives me too much, right? And so then I subtract the area left of negative 1.7, which is just this little area, and I'm left with exactly what I want, okay? So let's do that. Come over to Excel, and we've got equals norm dot dist 2.1, 0, 1, true, minus norm dot dist negative 1.7, 0, 1, and everything to the left, so true. And we get 0.9376. 0.9376. All right, so that is an introduction to mostly the standard normal distribution. Again, very mechanical. All I want you to be able to do is find areas under that curve. The reason being that those areas in the very near future are going to correspond to probabilities. And so if you would go ahead and try some problems on that and just be able to have those mechanics down, we don't want the mechanics, just the sheer, technical piece of computing these to get in the way of the deeper idea, which is that we're actually finding probabilities, and these can tell us important things. Next we're gonna look at some applications and taking areas maybe and finding what values go with those. That's next time. So for now, take some time to digest this, and I will see you soon.